This video is the second part of Bermudan Swaption pricing. In the previous video, we have discussed what path-dependent interest rate derivatives are and what an interest rate swap is and what a swaption is, the Bermudan Swaption in market and its key use cases, and the valuation challenge of the Bermudan Swaption, and the free boundary formulation, and at last, the Bellman's principle of optimality. In today's video, let's dive deeper into pricing the Bermudan Swaption. We will look at the Hull-White model and dissect it completely to understand how the process is done. To implement the Bellman equation, specifically to compute the conditional expectation that defines the continuation value, a model for the stochastic evolution of interest rates is required. The underlying of a swaption is an interest rate, which, unlike a stock, is not a directly tradable asset. Therefore, a consistent model of the entire term structure is necessary. To ensure arbitrage-free pricing, the one-factor Hull-White model is a widely used choice in industry and academia, offering a compelling balance between analytical tractability and key realistic features. The value of a swaption depends on the future value of an interest rate swap, which in turn depends on the entire future path of the yield curve. A stochastic model provides the engine for simulating these future paths under a risk-neutral probability measure, allowing for the calculation of expected values. The Hull-White model belongs to the class of no arbitrage models, which are specifically designed to be perfectly consistent with the yield curve observed in the market today. This is a critical property as it ensures that the model will, at a minimum, correctly price basic instruments like zero-coupon bonds. The Hull-White model describes the dynamics of the instantaneous short-term interest rate, RT, as a mean reverting stochastic process under the risk-neutral measure Q. Its evolution is governed by the following stochastic differential equation. So, the equation is dr of t is equals to theta of t minus a into r of t whole into dt plus sigma into dw of t. The key components of this equation are clear financial interpretations. R of t is the instantaneous short rate at time t. This is the single stochastic factor that drives the movements of the entire yield curve in this model. A is a positive constant representing the speed of mean reversion. This parameter captures the tendency of interest rates to be pulled back to a long-term average level. Sigma is a positive constant which represents the volatility of the short rate. dw of t is a standard Wiener process under the risk-neutral measure representing the source of randomness or shocks to the interest rate. Theta of t is a time-dependent function known as the mean reversion level. This is the most crucial component for ensuring the model is arbitrage-free. It is not a free parameter to be estimated, but it is instead a function derived analytically from the initial term structure of the interest rates observed in the market. A significant advantage of the Hull-White model is its analytical tractability. Despite its time-dependent drift, it retains many of the convenient properties of the simple basic model. The price at time t of a zero-coupon bond maturing at time capital T denoted by P of small t, comma capital T is equal to A of small t, comma capital T into e to the power of minus B of small t, comma capital T into R of small t, where B of small t, comma capital T is equals to 1 by A into 1 minus e to the power of minus A into capital T minus small t. And A of small t, comma capital T is another deterministic function that depends on the model parameters and the initial forward rate curve. This closed form solution is essential for calibrating the model's numerical implementation on a tree and for pricing other derivatives. Now, let's look into the model limitations. The model, while powerful, is based on simplifying assumptions. The first one is negative interest rates. As an extension of the Gaussian normal process, the Hull-White model allows the short rate to become negative. While this was once viewed as a major theoretical drawback, the experience of several major economics with negative policy rates in the 21st century has transformed this into a potentially desirable factor. The next limitation is its one-factor limitation. This is the most significant limitation, stating that the random evolution of the entire yield curve is driven by a single stochastic factor, dw of t. This implies that the random challenges in all forward rates are perfectly correlated at any instant in time. The process of fitting the Hull-White model to the market data is a nuanced two-tiered procedure. The first tier is the analytical calibration of the drift term, theta of t. This is the deterministic step, using the initial market yield curve to solve for the exact form of sigma of t that guarantees the model is arbitrage-free with respect to the bond market. The second tier is the market calibration of the dynamic parameters, that are the mean reversion speed A and the volatility sigma. These parameters are not determined by the yield curve. Instead, they are typically chosen by the user or optimized numerically to ensure the model provides the best possible fit to the observed market prices of a liquid interest rate options, such as the interest rate caps, floors, and European swaptions. To implement the backward induction algorithm for the Bermudan swaption, the continuous time hull-wide process must be discretized. A trinomial tree is a lattice-based method that provides a discrete time, discrete state approximation of the short rate's evolution. This structure is exceptionally well suited for pricing early exercise derivatives, as a backward induction logic can be applied directly to the nodes of the tree, naturally accommodating the optimal exercisation at each step. The direct construction of the tree for the hull-wide process is complicated by the time-dependent drift term, theta of t. The elegant solution proposed by Hellwhite involves a two-stage process. First, a simple time homogeneous tree is built for a base process. Second, the nodes of this base tree are shifted or displaced at each time step to match the initial term structure, effectively incorporating the time-dependent drift. The method begins by decomposing the short rate r of t into a mean reverting stochastic component xt and a deterministic displacement alpha of t. So r of t is equals to x of t plus alpha of t. Then the task is reduced to building the tree for a simpler process xt. The process x of t is defined as a simple Ornstein-Uhlenbeck process that starts at 0 and has a 0 mean reversion level. Therefore, d of xt is equals to minus a into x of t into dt plus sigma into dwt. The task is then reduced to building a tree for the simpler process xt and determining the appropriate shifts, which is alpha of ti, for each time step ti. The first stage involves constructing a recombining trinomial tree for the process x of t. A recombining tree is one where an upward move followed by a downward move leads to the same node as a downward move followed by an upward move, which is crucial for computational efficiency. The vertical spacing between the rate levels in this tree, denoted by delta of x, is equal to sigma into root over of 3 delta t. This is chosen to ensure the tree recombines and to match the variance of the underlying process. From each node I, j, 3 branches emerge, leading to nodes at the time step ti plus 1. The probabilities of these up, middle, and down moves, which are denoted by pu, pm, and pd, are calculated to match the first two moments, which are the mean and variance of the conditional distribution of x of ti plus 1 given x of ti, which is equals to x of I, j. For the Ornstein-Uhlenbeck process, the conditional mean and variance are expectation of x of ti plus 1 given x of ti is equals to x of ti into e to the power of minus a into delta t, and variance of x of ti plus 1 given x of ti is equals to alpha square by 2a into 1 minus e to the power of minus 2 into a into delta t. The probabilities are derived by solving the system of equations to match these moments. To ensure probabilities remain positive, different branching schemes and associated probability formulas are employed for nodes near the center of the tree versus those in the tails. For a central node, j, that branches to the levels j plus 1, j, and j minus 1, the probabilities are pu is equals to 1 by 6 plus 1 by 2 into aj into delta t square by delta x square minus aj into delta x into delta t by 2. Pm is equals to 2 by 3 minus aj into delta x into delta t square by delta x square. Pd is equals to 1 by 6 plus 1 by 2 into aj into delta x into delta t square by delta x square plus aj into delta x plus delta t by 2. With the symmetric tree for x of t constructed, the second stage is to determine the deterministic displacement alpha ti for each time step ti. This is done by a forward induction process that ensures the final tree of RT is perfectly calibrated to the initial market yield curve. The logic of this calibration is a sophisticated form of bootstrapping. In the same way that a yield curve is bootstrapped by sequentially using short-term interest rates instruments to price slightly longer-term ones, the algorithm uses the known price of bonds maturing up to time ti to determine the single parameter alpha of ti that forces the tree to correctly price the bond maturing at ti plus 1. This procedure weaves the entire market yield curve into the numerical model, guaranteeing no arbitrage consistency at every time step. The algorithm proceeds as follows. The first step is initialization at time t is equals to 0. At time t is equals to 0, the node is at x 0, 0 is equals to 0. We set the displacement alpha of 0 to be the initial short rate observed from the market yield curve R0. The initial state price is Q 0, comma 0 is equals to 1. The next step is called the forward step. Assume we have already determined the displacements of alpha tk for all k less than or equal to I. First, we calculate the state prices for all nodes at the next time step ti plus 1. A state price qi plus 1, comma k is a present value at time 0 of receiving $1 if and only if process reaches node I plus 1, comma k. It is computed by summing the contributions from all nodes at time ti that can transition to node I plus 1, comma k. So the state price can be written as qi plus 1, comma k is equals to sigma of qij into p of j tends to k into e to the power of minus j into delta x plus sigma into ti whole into delta t, where pj tends to k is a transition probability from state j to state k. The price of a zero coupon bond maturing at time ti plus 1, as implied by the tree, is the sum of all state prices at the time step. P of 0, comma ti plus 1 of the model is equals to sigma of qi plus 1, comma k on k. The model price must match the price observed in the market. The only unknown in the calculation of the state prices qi plus 1, comma k is the displacement alpha ti. We can therefore solve the equation for the unknown alpha ti, which then simplifies to this, allowing us for the direct solution of alpha ti. This process is repeated for I equals to 0, comma 1, comma 2, comma so on till n minus 1, moving forward through the tree until all the displacements of alpha of ti have been found. The final short rate at any node I, comma j is then given by r of I, comma j is equals to j into delta x plus alpha of ti. Once the calibrated hull-wide trinomial tree is constructed, it serves as a discrete map of all possible future interest rate paths and their associated risk-neutral probabilities. The backward induction algorithm is the direct numerical implementation of the Bellman equation on this lattice, allowing for the valuation of the Bermudan swaption by systematically solving the optimal exercise problem at each node. So the step 1 is initialization at the final maturity, which is capital T of n. So the valuation process begins at the time step of the tree, Tn, which is equal to n into delta t, which corresponds to the last possible exercise state of the swaption. At each terminal node, n, comma j, of the tree, there is no future optionality. The continuation value is 0. Therefore, the value of the swaption is simply its intrinsic value. So v of n, comma j is equals to max of 0, comma value of the swap at n, comma j. The term value of swap n, comma j represents the net present value of the underlying interest rate swap if the holder chooses to enter into it at this final node. This value is calculated based on the term structure of the rates implied by the subtree originating from node n, comma j. The core of the algorithm is a loop that iterates backward through time, from the time step I equals to n minus 1 down to I equals to 0. At each node I, comma j within this loop, the algorithm computes the swaption's value by applying the Bellman's optimality principle. For each node I, comma j at time ti, we calculate the continuation value. So the continuation value is given by this formula, which is equal to e to the power of minus r ij into delta t whole into pu into vi plus 1, comma ku plus pm into vi plus 1, comma km plus pd into vi plus 1, comma kd. Next, we check for the exercise opportunity. So this step depends on whether ti is one of the contractually permitted exercise states for the Bermudan swaption or not. If ti is not an exercise state, no decision can be made. The value of the swaption node is simply its continuation value. If Ti is an exercise state, the holder has a choice and the Bellman principle must be applied. This requires calculating the exercise value. This is the most computationally intensive part of the algorithm. The exercise value is the net present value of the underlying swap at node I, comma j. A swap can be valued as a portfolio consisting of a fixed rate bond and a floating rate bond. For a pair swaption, the value is V of swap is equals to V of float minus V of fixed. At a coupon reset date, the value of a standard floating rate bond is equal to the notional principal. The value of the fixed rate bond must be calculated by finding the present value of its remaining fixed coupons and principals. This requires a separate valuation procedure on the subtree originating at node T I, comma j. Specifically, a backward induction is performed on this subtree to price the remaining cash flows of the fixed leg using the discount rates from the tree itself. This reveals the deeply recursive nature of the pricing algorithm. The valuation of the complex derivatives necessitates the valuation of simpler instruments on the remainder of the tree. So the value of the Bermudan swaption at the node is the maximum value of exercising and the value of continuing. So the last step of this process is convergence to time 0. This recursive process continues until the loop reaches the initial time step I is equals to 0. The calculation at the root node of the tree 0, 0 yields the final result. The price of the Bermudan swaption at time 0 is V of 0, 0. So let's look at this small example to understand the valuation process better. The parameters are as follows. The short rate at node I, j is equal to 3%, and the time step is equal to 0.25 years. And the successive values, also known as the swaption values at ti plus 1, are equal to V of ti plus 1, comma ku is equals to 1.50, V of ti plus 1, comma km is equals to 1.20, and V of I plus 1, comma kd is equals to 0.90. The transition probabilities Pu is equals to 0.20, Pd is equals to 0.20, and Pm is equals to 0.60. So using these parameters, we can calculate the continuation value, which is equal to e to the power of minus r I comma j into delta t whole into Pu into Vi plus 1 comma Ku plus Pm into Vi plus 1 comma Km plus Pd into Vi plus 1 comma Kd, which is equal to 1.191. And let us assume that the NPV of the underlying swap at I comma j found via subtree evaluation is equal to 1.300. So according to Bellman's principle of optimality, V of I comma j is equal to max of 1.300, 1.191, which is equal to 1.300. So the final swaption value at node I comma j, denoted by V of I comma j, is equal to 1.300. In this example, since the exercise value exceeds the continuation value, the optimal decision at the specific node is to exercise the swaption. The value stored at this node for subsequent backward steps is therefore the exercise value. Now let's translate the theoretical framework and numerical algorithms into working Python implementation with careful consideration of the data structures and functional decomposition. The goal is to create a modular and understandable code base that mirrors the logical steps of the valuation process. This script implements the pricing of the Bermudan swaption using a trinomial tree to model the Hull-White one-factor short rate model. The implementation follows the logical steps described in the valuation process. So first we import the required libraries and functions such as numpy and kubecspline from the scipy.interpolate library and matplotlib.pyplot. Our objective is to walk through a complete Python implementation covering 4 key stages. The first one is defining the data structures for the market and instruments. The second objective is building and calibrating the trinomial tree via backward induction. The third one is pricing the underlying swap at any point on the tree. And finally, valuing the swaption itself using backward induction. So let's begin. A robust model begins with clean and logical data structures. We have defined 3 primary Python classes to organize our problem. The first one is a yield curve class. This object represents the market term structure of interest rates. It takes market maturities and the corresponding zero rates and uses cubic spline for smooth interpolation. This is our anchor to market reality. Any model we build must be consistent with the curve. Its key role is to provide discount factors P of 0, t for any maturity. The second is the interest rate swap class. This defines the underlying instrument. A swaption is an option to enter into a swap, so we need to define the swap's parameters precisely. Its notional, the fixed rate strike, its tenor or lifetime, and the payment frequency. Finally, we have the Hull-White tree class. This is the scaffold of a model. It holds the Hull-White model parameters A for mean reversion and sigma for volatility, and the tree's dimensions such as the time steps dt and the rate step dx. It also pre-allocates arrays for the short rates, the calibration parameters alpha, and all the important arrow-Debreu state prices. With our structure in place, we move to the core algorithmic components. This is the heart of the model construction. We build the short rate tree using a process called forward induction. We start at time 0 and step forward to the final maturity. The implementation of this follows the same procedure which we discussed during the construction of the Hull-White trinomial tree. At each time step I, the crucial task is to find the displacement parameter alpha. This alpha shifts the entire rate grid up or down. We choose alpha such that the price of a zero coupon bond within a model tree perfectly matches the price from the real-world market yield curve. This step, known as calibration, is what makes the model arbitrage-free. It ensures our theoretical tree is consistent with the market prices we observe today. As we move forward, we also calculate the arrow-Debreu state prices Q, which represent the value today of $1 received in a specific state in the future. Now let's go to the next function, which is price fixed leg bond on the tree. Now, why do we need this function? We're standing at a node on a tree on a potential exercise state. We must decide, is it better to exercise the swaption or to hold it? To make that decision, we need to know the value of the underlying swap if we were to enter it at that moment. The value of a swap is the value of its floating leg minus the value of its fixed leg. The floating leg's value is simply par or the notional amount. The fixed leg is the stream of constant payments, which is economically identical to a fixed coupon bond. This function does exactly that. It performs a standard backward induction on the subtree, starting from the node to calculate the present value of that fixed leg. Now, this is the final valuation step and function, the pricing Bermudan swaption function. We use backward induction, starting from the swaption's final maturity and stepping back to time zero. At the last exercise date, the value of a swaption at each node is simple. It is the intrinsic value, which is the maximum of zero and exercise value we calculate using our bond pricing function. Then we step backward at each node I, j. We calculate two quantities. The continuation value, which is the discounted expected value of the swaption in the next time step calculated using a risk-neutral probabilities. This represents the value of holding the option. And the exercise value. If the current date is an exercise date, we calculate the value of exercising immediately. Now, the swaption's value at this node is determined by the Bellman's optimality equation. It is the maximum of the exercise value and the continuation value. If it's not an exercise state, the value is equal to the continuation value. We repeat this process until we arrive back at time zero. The value at a single starting node is the arbitrage-free price of a Bermudan swaption. Now let's put this all together. We define a market with an upward sloping yield curve. We set the Helm-White mean reversion A to 0.1 and the volatility sigma to 1. Our instrument is a 5-year Bermudan swaption, exercisable annually. If exercised, it allows the holder to enter into a 10-year pay swaption with a notional of 1 million and a fixed rate of 4.5%. The tree needs to extend to the final maturity of the underlying swap, which is 5 years from the swaption start plus the 10-year swap tenor. When we execute the code, first the calibrated Hull-White tree is constructed. This can take a moment as it solves for alpha at each time steps. Once the tree is built, the swaption pricing function performs the backward induction. The final valuation is complete. Now let's run this. The final valuation is complete. The model calculates the price of this specific Bermudan swaption to be $66,713.61. In summary, we have successfully priced a complex early exercisable derivative. The valuation of a Bermudan swaption using a one-factor Hull-White model on a trinomial tree represents a cornerstone technique in the quantitative finance field. The final price obtained is the culmination of a sophisticated process that integrates financial theory, stochastic modeling, and numerical methods. However, the single numerical result is less important than a nuanced understanding of the model's behavior, its inherent limitations, and the pathways to more advanced approaches. The primary limitation of the one-factor Hull-White model is its foundational assumption that all random movements along the yield curve are driven by a single source of uncertainty. This implies that the changes in all forward rates are perfectly correlated at any given instant. In reality, the yield curve exhibits more complex dynamics. It can steepen, flatten, or invert as short-term rates and long-term rates move with a degree of independence. This simplification can lead to mispricing of derivatives whose value is sensitive not just to the level of rates but to the shape of the yield curve. While the one-factor Hull-White model sacrifices realism by using only one factor, its efficiency and intuitive connection to dynamic programming make it an invaluable tool and a critical subject of study. An expert analyst is defined not by the knowledge of a single best model, but the ability to understand these trade-offs and select the appropriate tool for the specific problem at hand.